Okay.
That's my paper.
Yes.
Okay.
Let's not make them fun of me.
We're just confused.
Are we okay?
Yeah.
We're gonna ask questions, but there's one.
I'm guessing
Let's talk about the yellow sheet first.
Big before me not having to accept.
No, fine.
Which sheet first?
The yellow.
But that's also
Fine.
tiny.
Okay, so here's the drill for the day. So we're gonna spend a lot of time talking about that assignment 2-1 from yesterday, the table of lines, equations, and graphs. So if you can do that, you should be feeling pretty good about the test, okay? Because that's what a lot of the test is going to be. So, couple of big items that'll be on the test. One of them is just gonna be like the vocabulary part of it. So here's how the test is going to play out. It's going to be the shortest test you're going to have. It's just one page front to back. The first probably 8 questions are going to be like multiple choice. It's going to start off and say, hey, let's talk about like, what's the difference between the independent and dependent variables, okay? So let's talk about that even in terms of that assignment. So you had, for example, on the back side, you had to graph force and acceleration. Okay, so let's talk about that, because I promise you, the test, part of this test is going to be, I'm going to give you a chart just like this. I'm going to give you a chart of force, I'm going to give you a chart of acceleration, and you're going to have to draw a graph, and you're going to have to tell me what the graph means. You have to calculate the slope. In what form do I not want the slope? Fractions. Abomination. Okay? Not leave that slope as a fraction. What else are you going to put on the end of that slope?
Units.
Units, because if you don't have the units, you don't know what it means. Okay? So, when you look at force and acceleration, which one is the independent variable and which one is the dependent variable? Nick.
Independent is the one you control, force and all
So is my independent variable going to be my force or my acceleration?
that.
Yeah, because here's the cart, right? So I can give a little bit of force to it, I can give it more force, that's what's going to happen. So that force is going to be your independent variable. That's going to get graphed on the y-axis. You're going to have acceleration here, be a linear function. Then you're going to find that slope. Now, what units is that going to work out to be? Well, what's your acceleration going to be in? Not meters. What's your acceleration going to be in?
Meters per second squared.
Meters per second squared. Okay? So there are certain things you should know absolutely. Okay? And if you're making index cards, you can do index cards. You should know the 3 fundamental units: meters, kilograms, seconds, mass, distance, time. You should know those. The 3 derived units: velocity, meters per second; acceleration, meters per second squared; force, newtons or kilograms, meters per second squared. That's one of the base things you have to know. Because if you don't know that, you can't do dimensional analysis. You can't figure out what the slopes of the graphs are. Okay? So if you make sure, and I don't care if you make index card that says, oh, here's an index card that says, hey, here's the 3 fundamental units, list the units on one side, list what they are on the other side. I don't care. Now, the reason that that's so important is because if you look at all the units we're going to use between now and probably the 1st of November, it's only going to be those 6. Okay, that's it. It's meters, kilograms, seconds, it's velocity, it's acceleration, force. Okay, that's it. That's why it's so important that you know those. All right, so I've got meters per second squared, and then I'm going to divide by kilograms meters per second squared, because that's what force is going to be used. These are going to cancel out, and I'm going to get 1 over kilograms. Does that represent mass? or the inverse of mass?
Inverse.
Inverse of mass. What's the only way it could represent mass? What would the units been? If the units had been kilograms, the slope would represent mass. But it's 1 over kilograms, so the slope represents the inverse of mass. So that's that answer to 11b on the back side, okay? So your slope, let me give you some hints while we're talking about number 11. Your slope should be less than 1. It should be 0 point something. So that answer to 11a should be 0 point something. It's going to be a decimal. Notice that on all the values that I gave you, there was 3 significant digits, which means your slope should have 3 significant digits. Okay, you might, let me give you a hint, you might have to chuck some zeros on the end to make that happen. Okay, so your answer to 11a should be a decimal with the units of 1 over kilograms. Okay, cool. On C, and I'm going to ask you a question like C. I promise you, it's going to be on the front of the test on this. It's going to kind of follow this sequence. I'm going to say, hey, write the general equation for the line. You could write, if you're into the y-intercept form, you could write y equals, boom, the slope, 1 over kilograms times x. If you like that. If you're like, oh, Mr. Burkamp, y equals mx, that's my love language. Cool. You're a nerd, but go with it. So if you like the y-intercept form, put it like that. You go, oh, Mr. Burkamp, I'm in a physics class. I want to put it in terms of physical quantities. Cool. So you could go a equals the slope, 1 over kilograms times force. Okay? I don't care. Pick one. I care not. Just make sure you put the units with the slope. Okay? Don't do dimensional analysis. Don't put in meters per second squared. Don't put in newtons. This is not dimensional analysis. It's just a general equation for the line. When you get to D, and say how much force would be needed to produce an acceleration of 6.5 meters per second squared. Oh, here's 6.5 meters per second squared. You're going to know that number. Divide that by the slope. You get an answer. Now, here's the story. And I promise you, you're going to do something like that on the test as well. So when you get an answer, how could you see if your answer seems reasonable? 1G.
Check it on the graph.
Yeah. So if you look at your data, you're at 6.5 meters per second squared, which is just beyond what 6 meters per second is. So you know a 6 meter per second squared acceleration requires a force of 30 newtons. So 6.5 meters per second squared is going to be a little bit bigger than that. So if your answer isn't a little bit bigger than 30 on that answer to part D, you've done something wrong. Okay? So when you get that answer, go back, look at your data, because all these are x and y coordinates that we call acceleration and force. Okay, that's it. It's a Cartesian graph. Acceleration and force, we just call them, instead of x and y, we call it acceleration and force. It's the same idea. Okay. And then I'm going to ask you this question. I promise you. I'm going to say, hey, what would happen to the slope of the graph? And again, I only have 2 options. I could say, what's going to happen to the slope of the graph if the mass increases? Or I'm going to say, what's going to happen to the slope of the graph if the mass decreases? Those are the only 2 tricks that I have. Okay, that's it. I can either ask you if the mass gets bigger, I could ask you if the mass gets smaller. There's 2 approaches that you can take. I care not, depending upon what level of math nerd that you are. Option number 1, you look at this graph and you go, well, if I apply the same amount of force, then the acceleration is going to increase or decrease, therefore the slope will increase or decrease. So one option is that you keep the force the same, you explain it that way, you say, oh, well, if there's less mass, that'll produce a greater acceleration. If there's more mass, it will produce a smaller acceleration. What's going to happen to the slope of the line? It's an option, okay? If you want to keep acceleration the same, you would say, hey, I want the same acceleration, but with more mass, that's gonna require more force. Oh, what's gonna happen to the slope of the line? That's an option. If you're a math nerd, if you realize that the slope of the line represents the inverse of the mass, okay, then you go, oh, right, if I take the inverse of a bigger number, the slope will become a smaller value. Okay? If you decrease the mass, you're taking the inverse of a smaller number, the slope would get steeper. So those are the two options that you have when you go to answer that question. It's going to be on the bottom of the front page. I'll even tell you where it's going to be. Okay? And I'm going to say, what's going to happen to the slope of the line? Mass increases, mass decreases. Keep the force the same, explain it that way. Be a nerd, talk about the inverse of the mass. I don't care. Okay? Now, if you're not sure, it's like, oh man, how am I going to remember that? In case you haven't noticed, I always get your assignments back to you. You have the problem. Okay? There's that page that was stapled together. It has the 3 graphs across the middle. Okay? You have that assignment. Go back, take that, change the numbers. Okay? Generate your own graph of force and acceleration. Redraw the graph. Play the what-if game. Okay, hey, what happened with the mass increases? What happens if the mass decreases? You have that assignment back. Go back, look at it, cover it up with a piece of paper, work the problem again. Because you know that question is going to be on the test. The only thing that I can do is change the relative values of acceleration and force. That's the only thing that I can do. Okay, I don't have that much variation on the theme. That's the only thing that I can do. Okay, so you know that's going to be on there. All right. Speaking of dimensional analysis, let's talk about number 4. So on number 4, so you have D equals kV squared. Okay? So this is this process of dimensional analysis. And I promise you, there's going to be at least one, if not 2, problems where you have to do dimensional analysis. Dimensional analysis, I emphasize this again and again and again and again and again, is a process, okay? It isn't just, oh, I'm going to write down units and a miracle is going to happen and then, oh, it's a valid equation, okay? It's a process. You show how things cancel out. So let's start with this. Let's say this is the question on the test. What's the first thing you're going to do? First step. Rhymes with substitute units. Substitute units. Brilliant one, G. So, this is going to be meters equals K. Then I'm going to have velocity in meters per second, but that's going to get squared. Okay? So then, if it were me, I'd rewrite this as D equals K, and then I'm going to have meters squared over second squared. Okay? Cool. It's the first thing you have to do. Now, you want to get K by itself. You can do this one of 2 ways. You can either divide both sides by meters squared over second squared, which is cool, but that gets a little sketchy in terms of trying to get things to cancel out. What I would do, if it were me, I'd multiply both sides because I'm trying to isolate a variable. I'd multiply both sides by the reciprocal, that's meters, of second squared over meters squared. So then everything over here is going to cancel out. And now I've got second squared over meters squared times meters. Okay? That's what I got. So what are you going to end up with? Second squared over meters. Now, here's how you can tell that this is right. Take what you think you have for K, substitute it back in, multiply that by meters squared over second squared, and see if you get meters. If you do, very, very, very high possibility that it's right. If you don't produce units of meters, I promise you it's wrong. Okay? So, that's what you got to be able to do. Right. Now, I'm going to say, what does this represent? Oh, because it's seconds squared over meters, it represents the inverse of acceleration. Okay? If it had been seconds over meters, it would have been the inverse of velocity. Okay? Cool with that? We're good. I promise you, I promise you, I promise you. Going to do stuff like that on the test. Now, let's talk about number 6. So number 6, you've got this v squared equals v naught squared plus 2ad. Once we get into acceleration, so we've got the next unit of velocity, then after that we have acceleration. So this is what's known as that equation, okay? Started this way many years ago. I'm just going to plant the seed now. This is the only equation that has a name, and it's that equation. Okay? Go to anybody that's had for physics before, go, oh, what's that equation? V squared equals V naught squared plus 2ad. So, bless you. So, you want to solve this thing for V naught. So what's the first thing that you're going to do? Bennett, what's the first thing I'm going to do?
I'm gonna get the 2AD out of there, subtract to the other side.
So I'm going to have V squared minus 2AD equals V naught squared. Then what am I going to do? Kelvin, what am I going to do next?
Root both sides.
Root. Sounds kind of funny. Root it. Root 18. Go physics. So I've got this, V squared minus 2AD. Now, here's the $1 million question. Can I go, ooh, what's the square root of V squared? Can I write that as V minus the square root of 2AD? Can I do that? Jane?
No.
Why not? Looks cool.
Yeah, but the minus sign.
Minus, that's so nice. No, this is as far as you can go, right here. Okay, this is it. This is it. If you have V minus the square root of 2AD, you took that simplification too far. Okay, and here's the reason why. What's the square root of 4? Or?
-2.
-2. So here's why you don't want to do that. It's because then you would have, if you did this, you wouldn't know whether to take the plus or minus value of that, the plus or minus value of that, and the fact that, like Jane said, it's just underneath the radical. So that's why you can't simplify this thing down anymore. Okay? That's why. You just have to leave it as V squared minus 2AD. That's it. That's all you can do. Don't simplify it anymore. Okay? Now, here's kind of a sketchier one. Now, I'll just give you a hint. So when you get to 7c, and you got distance equals 1/2 AT squared plus V naught t, and you want to solve this for A, okay? Now, this is what I would do. Take this for what it's worth. I hate fractions. So what do you think the first thing I'm going to do is?
Make that a 0.5.
What'd you say?
Make that a 0.5.
No. That's not going to, no. How can I get rid of fraction, that 1/2? I multiply everything by 2. Okay? I would multiply everything by 2. That eliminates the fraction. But you have to multiply everything by 2, because it's all about equality. Okay? You have to multiply everything by 2. Then you want to get this A by itself. So at that point you have 2D equals AT squared plus 2V naught T. Then what could you do? Subtract it and then divide. So if you want some dimensional analysis practice, take your answer to 7C, do dimensional analysis, and see if you get meters per second squared. Okay? And that's nice because you have to do some subtraction and you have to do some division. Now, let's just say you have this. I'm just going to throw this out there as a possible, because I've seen this answer before. Let's say that I have D minus V naught over T squared times 2. let's say you have that. Right away, why do you know this equation won't work? This is a train wreck, and I can look at it and go, it's a train wreck. Jackson, what units is distance measured in?
Meters.
So I got meters here, right? What's my velocity in?
Meters over seconds.
Meters over seconds. Right away, this is the Titanic. It's gonna sink. Why?
You can't subtract. that
Yeah.
distance from it.
I can't take a velocity and subtract it from meters. Okay? Right away, as soon as I see that, I know this equation is wrong, because I can't subtract the velocity from a distance. But, what if I had this? 2 minus v naught t over t squared. What about that? How's that looking? London.
Better.
Better. That's the most non-committal answer. Better.
Because
But she said it with such style and grace. Better. So, London. Why is it better?
Because it's meters minus meters over seconds times seconds. So the seconds cancel out and it's meters minus meters.
Ah, this is why it's better. Because then you would have meters per second times seconds. What London said, the meters cancel out. Then would I have meters minus meters? Yes. Is that in our wheelhouse? Yes. Because then I'd have meters divided by what?
Second squared.
Second squared. Is that what acceleration is then? Yes. Okay? So that's a kind of, again, once you kind of embrace this idea of dimensional analysis, it kind of becomes second nature. It's like, okay, let me look at this and see if it works. Okay? If it does, hey, you got a fighting chance. If it doesn't, if the dimensional analysis doesn't work, there's literally no point in plugging the numbers into your calculator, because your answer that you're going to get, I promise you, is wrong. Okay? It's not going to work. Okay. So let's talk about number 8. So on number 8, you have the period of a pendulum. We'll spend some time talking about this once we get into gravitational fields, because this is a pendulum equation, okay? So like this thing is swinging back and forth. So the reason that we use uppercase T is because it's the time it takes to go from one side back to the other like this, okay? That's the only thing that you've got. So one of the things you should be able to do is look at this and go, what's a factor in this equation? So if I swing that pendulum like this, or if I swing that pendulum like this, which one's going to have the longer period? This one? Or that one? Or is it the same?
It's the same.
It's the same. Why?
Same length of the string.
Yeah. What are the only two things that determine the length of the pendulum? Or, excuse me, the period of the pendulum. The length and gravitational acceleration. That's it. The amplitude of the swing doesn't fit into that equation at all. Does the mass of the rubber stopper on the end be a factor? Nope. It's only L and G. That's it. Okay, that's it. There's nothing else. That's it. L and G. So, according to the legend, who came up with that was Galileo. According to the legend, he was sitting in a church. And at the time, this is 1600s, no heating and air conditioning. And they had the windows open because it was hot, and there was a big chandelier. And he noticed that was swinging back and forth, and he used his pulse on his hand to determine the period of the pendulum. And what he observed was that even when the wind died down, and it was still moving, but not as much, it had the same period as when the wind was blowing, and there was a bigger amplitude going back and forth. So that's kind of the base, that's the historical basis of this equation. So, here's the story. Here's what I'm going to tell you on 8A. You should have L equals something, okay? And there should be a 4 pi squared somewhere in your answer. So here's how you can check that your answer to 8A is right. Do dimensional analysis and see if you get units of meters. If you get units of meters, if you do dimensional analysis, you at least have a fighting chance. If you do dimensional analysis on 8A and you don't get meters, I promise you it's wrong. Okay? I promise you it's wrong. So let me give you a hint. Your answer to 8B on the top of that back side should be, and this is an ish, okay? It's an ish. It should be around 0.5 meters. Okay? That's an ish. All right? It's an ish. 1G, are you?
We're close.
We're close?
No, we're not.
Okay, because I saw you going,
Tony and I were just talking about this one, and we were
And
fighting
she said I
the
was
answer.
wrong, and I had 0.5 something.
Okay, well, I'm just not very good at that. That's
So-
okay. I'll
And I
figure it
believed
out.
her, because her calculator.
okay, Scout's honor? Okay.
I'll figure it out.
Okay, I have no doubt. Okay? And that's typically what I'll do, is I'll say, hey, the answer is somewhere around this. Okay? Now, when you get to 8C, you're going to have this solved for little g. And again, your answer to 8C should involve a 4 pi squared, pencil down, should involve a 4 pi squared somewhere. And again, your answer to 8C, if you do dimensional analysis, what units should you get? You're trying to solve for an acceleration. What should you get? Meters per second squared. And that's the only way, in terms of this, the only way you can do this is if you have L over T squared. So your answer to 8C, again, let's say you're going, man, I don't know how to solve this. You know you have to end up in meters per second squared. The only way you can end up in meters per second squared is if you have L over T squared. Now, there's a 4 pi squared lurking in there somewhere. You have to figure out if it's at the top or the bottom. So, this is the historical perspective of this equation. Let me give you the hint. The 4 pi squared shows up on top. So, when we went to the moon, and we'll talk more about gravitational acceleration and all these equations later on. When we went to the moon, we didn't know the exact mass of the moon. Okay, we had a pretty good idea, but we didn't know the exact mass of the moon. So one of the things that the Apollo 11 astronauts did when they were on the moon, one of the science experiments, is they literally set up a pendulum. They set up a pendulum of a known length, and they measured the period of the pendulum. So what they were able to do by doing that is that they discovered the value of little g on the moon. Guys, because when we landed, we didn't know exactly what it was. Okay? We landed, we did this experiment. Literally, they set up a pendulum. They knew the length, they took a stopwatch. Counted it, boom, plugged it into this equation. They found the value of little g on the moon. From that, there was a much bigger equation that they plugged this value of little g in to actually find the mass of the moon. So we found the mass of the moon using a pendulum. Okay? And that's a cool part about science. So how do you find the mass of the moon? Set up a pendulum. Great. Okay. Find little g. Then if you know the radius of the planet, you can find the mass of the planet. So that's the significance of that. Your answer to 8D should be a fairly decent GPA. Not horrible, not absolutely stellar, but not bad. Okay? Not bad. Huh?
That sounds pretty good.
Okay. Well, it's a relative term. Some people would be disappointed with that GPA. Others would be going, score! So that's why I said it's relative. Okay? Cool with that one. Now, let's talk about number 9. I promise you, Scouts Honor, okay? Scouts Honor, 1G, Scouts Honor. You're gonna have a problem like number 9 on the test. I promise you, okay? If you hand in the test and you haven't done a problem like number 9, you have done something horribly wrong. And I'm even gonna give you that 2 pi r over t equation. Don't memorize it. It's gonna be on the test. I'm gonna tell you using this equation, okay? Using this equation. You're gonna hit it, here it is. You just have to know what to do with it. I'm gonna pick a planet, Mars, Venus, Jupiter, or something like that, okay? Now, and don't get wrapped up and go, oh, man, that's a tough equation. I've never seen that before. Literally, all this is this idea that I'm gonna swing something around, it's gonna travel in a circle, and we're gonna measure how long it takes to go around. That's it, okay? The 2 pi r is just the circumference of the circle. It's how far it goes. Period is just how long it takes for it to go around, okay? So don't look at this equation and go, oh, this organic physics is hard. It's distance divided by time, okay? That's it. Don't make it complicated. So here's what you need to do. Pay attention to the units. So on number 9A, here's our star, here's our rock, and our rock conveniently orbits around our star in what we call the Goldilocks zone. If our rock was much closer, we'd be too warm, we probably wouldn't have oceans. If we were much further away, we'd be too cold, and the oceans would be chunks of ice, okay? So we're like in this sweet spot, okay? Literally, it's called the Goldilocks zone, okay? Not too close, not too far away, okay? We're just right. We got lucky. That's it, we just got lucky. So, you're gonna take the 2 pi, pay attention to the units. I've given you the radius 1.50 times 10 to the 8th kilometers, okay? You don't have to do anything with that, it's in kilometers, okay? Because the first answer you want is in kilometers per hour. Now, our rock takes 365 days to go around. 1 day, 24 hours, okay? So, that's it. So there's a couple ways you can do this. If you only take 365 times 24 and get that number by itself, cool. If you want to do this all at once and plug it into your calculator, cool. If you're going to do it all in one step, though, on your calculator, word of caution. When you hit that divide button, you have to put the 365 and the 24 in brackets, okay? So that it mathematically is treated as one entity. If you just put in divide by 365 times 24, that's what it's going to do. It's going to divide first, and then it's going to multiply by 24, okay? Instead of dividing by 365 times 24. So if all goes well on number 9, that first answer in kilometers per hour should be around 1 times 10 to the 5th kilometers per hour. Okay? 1 some change times 10 to the 5th kilometers per hour. Okay? Now, then you want to convert that into meters per second. So this is what I would recommend. You got 1.0 something times 10 to the 5th kilometers per 1 hour. Okay? That's what the number means. It's kilometers per 1 hour. Put the 1 hour down below. Okay? Because that's what it means. Cool. 1 kilometer, 1,000 meters, 1,000 meters. 1 hour is 3,600 seconds. You really want to get fancy, you can lop off zeros. Short version is, you convert from kilometers per hour to meters per second, multiply by 10, divide by 36. That's it, okay? Every conversion from kilometers per hour to meters per second is this. You multiply by 10 and then you divide by 36. Okay, that's it. Times 10 divided by 36. What that means is that your answer in meters per second is that always going to be bigger or smaller than the numeric value in kilometers per hour? Smaller. So your answer to that second part on B should be around 3 times 10 to the 4th meters per second. Okay? It's a ballpark. Should be around 3-ish times 10 to the 4th. Now, don't forget these rules of significant digits. On number 9, how many significant digits should your answer have? Bless you. You're welcome. 3, because you have 1.50 times 10 to the 8th kilometers. Okay? Cool with that. Now, let's talk about number 10. The answers to 10 created a problem. Okay? It really did. So, here's our rock. Okay? And conveniently, we're tilted, so therefore we have seasons. If we weren't tilted, if we were spinning around the Earth like this, and that was at a 90-degree angle to the plane of the orbit, we would never have seasons. Daylight would be 12 hours, sunlight would be exactly 12 hours, okay? We would not have seasons. Wouldn't have to worry about changing clocks. There would be no autumns, like pumpkin spice lattes, okay? So, that really wouldn't bother me. But here's the point, was that we wouldn't have seasons. Now, conveniently, we're not tilted so far that we're spinning like this as we go around the sun, because if we were spinning like this as we go around the sun, half of it would be in daylight, the other half would be in the shadow, and that would be it. Like, you'd either be hot or cold, okay? That would basically, those should be your two options, okay? So conveniently, we're tilted. We have seasons, but not extremes of seasons. Now, how long does it take for our rock to spin on its axis? 24 hours, okay? So, you're going to do that same thing. You can go V equals 2 pi r over t. So now we're talking about, you're here, we're going to spin on its axis. How long is that going to take? Oh, that's going to take 24 hours. 2 pi, boom, you have your kilometers. So that first answer should be on number 10, should be a not so good GPA times 10 to the 3rd. Okay? Not so good GPA times 10 to the 3rd. Now, I'm going to tell you straight up, your answer in meters per second should be about 463 meters per second. Now, let me explain why this became very problematic. Okay? Once we figured this out, once we figured out like the circumference of the Earth, which is a cool story, it had to do with this is in like ancient Egypt. There was on a particular day, there was a well, and on one day of the year, the sunlight shined straight down into the well. And over here, at a certain distance away, there was a tower, and that tower cast a shadow on that same day. So, doing some simple geometry, they knew the distance between those 2 points. Then they were able to work out basically the arc length of that part of the circle, and then from there they were able to extrapolate the circumference of the Earth. Okay? They were actually pretty close. Kind of a cool deal. So, once they started to do these calculations and go, it takes 24 hours, here's the circumference of the Earth, like, wow, we're spinning really fast, right? So right now, that's at the equator. We're up here in Mesoamerica. Right now, we're going at about 400 meters per second. Now, to give you some perspective, the speed of sound is about 340 meters per second. Okay? That's the speed of sound. We're going at about 400 meters per second right now. But you don't feel it. It's like, oh, I feel it now. Wow, it's really fast. Okay? So there's a couple of things that work to our advantage. Number one, our atmosphere is also moving at 400 meters per second. Okay? Our atmosphere is moving with us. If the atmosphere wasn't spinning at the same rate, I'm guessing, hopefully at some point, this still happens. You're being driven around as a youth, minivan, something, SUV, car, horse and wagon, I don't know. And this is back when you were still willing to experience the outdoors, and maybe you had the window rolled down, and you'd put your arm outside the window. Anybody ever do that? Okay, thank God some of you have experienced the world. Okay? Now, did you ever do this? Trying to be that cool? Yes. That cool. Now, you were going probably about 40 miles per hour, okay? Which would be about 20 meters per second roughly. And you put your arm out and like, oh, you felt that. Okay, cool. So imagine our Earth is spinning and we're going about 400 meters per second, but the atmosphere is stationary. So you would be moving 400 meters per second through a stationary atmosphere. Bad things are going to happen. Okay? Like, bam, birds would not be able to fly. Trees would not be able to grow. You step outside, it's like, bam, you're just going to get knocked down. And it was also cool because you break the sound barrier as soon as you step outside. It's like the ultimate alarm system for a school. Did the door go off? No, but somebody broke the sound barrier, somebody escaped. Okay? So, conveniently, our atmosphere spins with us. Okay? It's cool, right? But here's where this became problematic. Again, if you hearken back to the days of your misspent youths, okay? Anybody here ride a bicycle in your youth? Okay, cool. Kendall, you strike me as a rebel. Did you ever, against your mother's wishes, ride your bike through a puddle of water? Probably. Let's go with yes, you did. When you did that, did the water stay on your tire or did it go flying off? It went flying off. Okay? Went flying off. And I'm guessing your tire might have been going 10, 15 meters per second. So this is where this became a problem. It's like, whoa, we have oceans. We have oceans. We had a lot of water on this strange rock. That's another issue we don't have. It's not like, where did all the water come from? It's like, we don't know. Glad we have it. We really don't know where it came from. UPS, I'm not sure. But somehow or other, we ended up with a lot of water. So that became the calculation. It's like, dude, we're going 400 and some odd meters per second. How can we have oceans? Why hasn't all of that water gone flying off the surface of the earth just like it went flying off of Kendall's tires when she rode it through a puddle of water? And that was only like 15 meters per second. This is like 400 and some odd meters per second. It's like, whoa, this is a problem. We should have oceans. All that water should have gone flying off. But what do we have as a strange rock? What do we have that Kendall's tires don't have? We've got gravity. Okay? We've got gravity. And we'll do these calculations later on. We have enough of a gravitational field to hold that water on. Okay? But it does distort the shape of our Earth. The Earth is actually a little bit flatter on the top and bottom of the North and South poles and we bulge out a little bit in the middle. Okay? So you bulge out a little bit here, we're a little bit flatter there. So, what, 1G?
Oh, I just said flat earth.
Oh, God, no. No, just say no. It is disturbing the number of people that even, consider that. It's like, really?
So you're not a flat earth.
I mean, I think you just kind of said it.
There's so many things. Just stop. It's like, just stop. Anyway, that's a whole. We'll save that argument for when we get into.
Sorry, my bad.
No, it's okay. I had a buddy of mine. Well, was a former student, Jared Gearhart, and he texted me one night. He goes, "Burkamp, I'm sitting in the driveway talking with my neighbors, and they're flat earthers. What can I do to counter their arguments?" And I just want to say, just walk away, because you're not going to win. So, anyway. All right, so let's talk about number 12. Speaking of flat earth or round earth, okay? So, here's the setup on number 12. So, the rock that we're on is round, okay? Let's go with that. Supposedly. Let's go with that argument. And so you're gonna make this beam of light go around our rock. And all this is again, is that velocity is distance divided by time. That's all this problem is, okay? That's all the problem is. But because we're going around a rock, instead of distance, what are we gonna use? 2 pi r. And since we're talking about the time for it to go all the way around, we're going to use uppercase T. I've given you the velocity, I've given you the radius. What's the only thing you don't know? It's T. Now get out of this habit of putting in the numbers and then solving the equation. You are not a squirrely little 8th grader or freshman in Algebra 1. You are running with the big dogs. Okay? Solve the equation first. It's going to save you so much pain and suffering in the long run. And the sooner you embrace this, the better off you're going to be. So, I've got V equals 2 pi r over t. That's what I've got. Okay? That's what I've got. How can I get t by itself?
Divide by 2 pi r.
No, God, no. No, bad. You can do that, but it is going to lead you into a rabbit hole of pain and suffering from which you might not escape. And you're going, wow, that really wasn't what I expected as an answer. Thank you, Mr. Brooke. I really wasn't expecting pain and suffering from that option. Avery, what can I do? I want to get t by itself.
Multiply t over.
Fantastic. Then I've got Vt equals 2 pi r. Then what am I going to do?
Divide by v.
Divide by v. There you go. It's much simpler. You would have just ended up in pain and suffering. That's what's it. Now, what units should you get out of this? London.
You should get
Can we articulate?
seconds.
Spell that if you can.
SECONDS.
That's how you spell it.
Yes.
Weird. I heard BL blah blah. You whatever. Okay.